All right, let's jump right into it. Welcome to this high-energy chemistry explainer. Look, if you've ever felt completely lost in the world of atoms and equations, you are in the perfect place. Today, we're going to break down the core, foundational concepts of chemistry and make this microscopic world completely crystal clear for you.
So let's kick things off with a kind of funny question. If someone takes up a massive amount of space in your heart, are they considered matter? Think about it. We say stuff like, you matter to me all the time. But scientifically speaking, do your feelings actually count as matter in chemistry?
Well, to answer that, here is our roadmap for today. We are covering 1. Matter, atoms and ions. 2. Molecules, compounds, and mixtures. 3. The laws of chemical combination. 4. Relative atomic mass. And finally, 5. The mole concept.
Starting right off with Section 1, matter, atoms, and ions, the literal building blocks of the universe.
The absolute crucial point here is this. For something to actually be considered matter, it absolutely must occupy physical space and have physical mass. So going back to our question, feelings like love, hate, or, someone taking up space in your heart, not matter. They don't have physical mass or take up physical volume, completely unlike the atoms that make up the chair you're sitting on or the air you're breathing.
Now, if matter is made of atoms, what are atoms made of? Subatomic particles. Electrons carry a negative charge, specifically negative 1.6 times 10 to the power of negative 19 coulombs. Protons, they have that exact same value but positive. And neutrons, just like the name implies, are perfectly neutral, zero charge. This is exactly why your standard atom, which has equal protons and electrons, has a net charge of absolute zero. The positive and negative values just completely cancel each other out.
But here's where it gets interesting. What happens when electrons, which sort of hover far away from the dense nucleus at the center, are transferred? Because they absolutely can be lost or gained. If an atom loses an electron, suddenly the positive protons outnumber the negative electrons, right? That creates a positively charged ion called a cation. On the flip side, if it gains extra electrons, the negative charge wins out, creating a negatively charged anion.
All right, let's actually test this out really quick. I want you to think about this. If a normal nitrogen atom usually has 7 electrons and 7 protons, how many electrons are sitting inside a nitride anion that has a negative 3 charge? Take a quick second to do the math.
Okay, if you guessed 10, spot on. You nailed it. That negative 3 charge literally means the atom gained 3 extra negatively charged electrons on top of its original 7. 7 plus 3 equals 10. Brilliant job.
Moving right along to Section 2, molecules, compounds, and mixtures. Let's see what happens when we combine these building blocks.
There is a golden rule when it comes to chemistry definitions. When atoms join together, they form molecules. Now, this could just be 2 of the exact same atoms, like oxygen gas, O2. But when different types of atoms join forces, like hydrogen and oxygen making H2O, we specifically call that a compound. So your big takeaway here, all compounds are molecules because they're groups of joined atoms. But not all molecules are compounds because compounds strictly require different types of atoms to be mixed together. Make sense?
And what about when stuff physically mixes together without actually chemically reacting? Well, we get mixtures. The best way to think about this is imagining making a massive pot of tea. When you dissolve sugar into that tea, one single spoonful tastes exactly the same as the whole pot, right? That is a perfect homogeneous mixture, completely uniform. But if you try mixing sand into a glass of water, that heavy sand just sinks to the bottom. That uneven, gritty mess, that's a heterogeneous mixture.
Section 3, laws of chemical combination, the actual rules governing the chemical universe. Over the years, scientists didn't just guess how reactions work. They observed highly consistent patterns and established these foundational laws. We're talking conservation of mass, constant proportion, multiple proportion, Avogadro's law, and Gay-Lussac's law. These are the rules that govern everything from preserving mass during a reaction down to the volumes that gases take up.
Let's zero in on one of the most important ones, the law of constant proportion. Going back to our tea analogy for a second, just like scaling up a tea recipe for 9 people means you keep a constant 1-to-1 ratio of milk to sugar, a chemical compound always maintains the exact same ratio of its elements. Take carbon dioxide. The mass ratio of carbon to oxygen is always 3-to-8. Whether you have one tiny molecule of CO2 or a million of them, that 3-to-8 mass proportion never, ever changes. Which brings us to Section 4,
Relative atomic mass. How exactly do we go about weighing the invisible?
Imagine being locked in a completely empty room with 5 different size boxes and absolutely no weighing scale. How do you figure out their weights? Well, you'd probably just pick one box, call it your baseline, let's say 1 unit, and then weigh all the other boxes relative to it. Okay, this box feels twice as heavy, so it's 2 units. Believe it or not, this is exactly how scientists figured out relative atomic mass. They originally used hydrogen as the baseline, but eventually shifted the standard to be exactly 1/12 the mass of a carbon-12 atom.
This super clever relative comparison gave birth to a whole new unit, the AMU, or atomic mass unit. Decades later, when we finally invented incredible tech like mass spectroscopy, we figured out exactly what that AMU converts to in physical grams. And guys, it is an unbelievably tiny value, 1.66 times 10 to the power of negative 24 grams, literally microscopic.
But there's a slight catch when weighing atoms. Some elements actually exist in slightly different natural forms called isotopes, which happen to have different masses. Take argon, for example. It has 3 different isotopes. So what's its official mass? To solve this, scientists calculate an average atomic mass. They simply take the distinct mass of each isotope, multiply it by its percentage abundance in nature, and add them all together. It's a really elegant mathematical trick to find a single usable mass for an element.
Finally, Section 5, the mole concept, bridging the gap from microatoms to macrograms. So, once mass spectroscopy actually allowed us to weigh a single carbon atom, we found out it weighs exactly 1.9924 times 10 to the negative 23 grams. That decimal is just absurd. Scientists quickly realized it was absolutely impossible to memorize that, let alone do daily lab calculations with the absolute masses of individual atoms. So, what was the brilliant workaround? Instead of struggling with the weight of one single atom, what if we grouped a massive number of atoms together? Think about it. If you group enough atoms, those tiny, impossible decimal values will eventually just multiply out into clean, workable, everyday whole numbers in grams.
And that exact massive quantity? It's 6.022 times 10 to the 23rd power, the legendary Avogadro's number. And no, it wasn't just picked at random. It was derived directly by figuring out the exact number of carbon atoms sitting inside exactly 12 grams of pure carbon-12.
We call this colossal group of atoms 1 mole. So the crucial, absolutely vital point here is this. When you look at a periodic table and see that sodium's mass is 23 grams, remember, it is actually 23 grams per mole. That is the physical mass of an entire Avogadro's number worth of sodium atoms sitting in a pile, not just one single solitary atom. This one concept is literally what allows you to weigh out powders on a scale in chemistry class and know exactly how many atoms you're holding in your hand.
And just like that, we've reached the end of our foundational journey. I really hope this power-packed explainer cleared up some of those tricky basic concepts and got you ready to completely smash your 2026 exams. But before we wrap up, I want to leave you with a quick, provocative thought. If you can hold an entire mole of water in the palm of your hand, just how many microscopic universes are you truly holding? Think about it, keep revising, and I'll see you next time.